So where was I? So let me just go through that. Consider the ground like this and the z coordinate pointing up. The Bernoulli equation for the statics, fluid statics, is dp dz equal to minus rho times g. Now we know that rho reduces with altitude. So essentially we have a reduction of rho with altitude, and rho is not a constant for the gas. So in order to perform the integration over z, so that is dp dz equal to minus rho g, we will integrate everything over z. We must know the nature of variation of how rho and g vary with z. We have already discussed yesterday that g remains more or less constant even up to a height of say 20 kilometers. But rho is in fact not a constant, rho reduces. So how does rho reduce? Now instead of explicitly specifying how rho reduces with z, we can say that as the pressure will also reduce. So suppose this is the curve for rho, this is the curve for pressure. So we can say that as pressure also reduces, the rho also reduces. So there must be some relationship between pressure and density. There must be some relationship between pressure and density. That relationship is the ideal gas equation, if you want to make that assumption, or in general it can be an equation of state. So ideal gas equation is one such model of the equation of state. So equation of state, you can have the virial expansion and all that. You can have any complicated equation of state. But essentially the equation of state gives us a way of relating pressure and density. And ideal gas equation says P equal to rho RT. So as pressure reduces, density also reduces. Conversely, if density reduces, pressure also reduces. So then we have dP dz equal to, now instead of rho, I will write it down in terms of pressure. So minus P upon RT dz. Now we can finally make this integration as we had done in the last class. Okay. So what, any doubt in this so far?
Sir, I was like temperature. I mean, if pressure increases, density increases, then temperature should also. I mean, we are assuming temperature to be constant.
Yeah, so the point is temperature is also a function of Z. But when we do a first course or a first kind of derivation, we can assume isothermal atmosphere. That assumption is actually called as isothermal atmosphere. Meaning, if you take a parcel of gas from here to here, that parcel of gas, that motion, that transfer of parcel of gas from one altitude to another altitude is done in an isothermal manner. This assumption is not entirely correct, but it gives an estimate of the altitude of the atmosphere. Apart from this, there are other assumptions also. One assumption is adiabatic atmosphere. Where instead of having T equal to constant, we have a variation of T with altitude. I mean, not just altitude, with pressure. So what is the relationship between P and T for an adiabatic process? Who can tell me the relationship between P and T for an adiabatic process?
P big power gamma is equal to constant. Then P something.
What is
Power
that
1
sum?
T power 1 minus gamma.
T gamma minus 1.
It's one constant.
So P raised to what?
T raised to 1 gamma minus 1.
P raised to gamma minus 1, T raised to?
No sir, P raised to 1.
So P raised to 1 is just P.
P raised to power 1 minus gamma into T to power n.
Gamma
Yes.
into T power gamma is
So then instead of putting temperature as constant, you will actually put temperature as a function of pressure and find out the variation of pressure. All right. So
Is adiabatic, like assuming that the process would be adiabatic is correct, like
yeah,
not the process.
that is actually not entirely incorrect, because when you take a parcel very quickly to altitude, you do not allow it enough time for exchanging heat. Okay, the temperature may change because of the change in pressure, but you are not allowing a lot of time for exchanging heat, and that is a fair assumption. That is a fair assumption. Okay, many thermodynamic processes are approximated as adiabatic process. Processes which are typically very fast can be assumed to be adiabatic. Okay, acha. Mm, over here, let us yeah, about the temperature and the lapse rate. So like we discussed, the temperature can also be given explicitly as a function of z without due course to what kind of process is going on. So the temperature can be given as beta naught minus sorry, T naught minus beta z, and this particular beta is known as the lapse rate. It is extremely important for a host of geophysical calculations. Okay, but let us not discuss this any further. It will be there like a essay kind of question. So now the questions have to be made a bit tricky because I have to evaluate you apparently. So I have to also give in a lot of thought behind making a question. And I hope you are doing it honestly. Look, I can in no way come to your home maintaining social distancing and all. I cannot check what is going on. But I hope you are maintaining the ethos of an assignment. And it will be clear once I start checking, it will be clear. And remember, I mean, if you are found to be copying, you will be in big trouble. And I'm sure you no one has copied. You are very honest people, right?
yes, sir.
Okay, good, good.
Of course, sir.
Yes, yes. Okay, let's continue with the fluid statics. We have the topic of manometry, a very useful thing to know, despite there being various advances in pressure transmitters, digital electronics, and all that. But regardless of that, manometry still holds a very useful place in engineering, in hydraulic engineering and stuff like that. Acha, have you ever seen how they find the level of bricks at a construction site?
Tube filled with
Water
water
level.
and like tip, and they place the both the ends, and by that they measure the difference between the
Very
level
good,
of water.
very good, very good. So there is a long transparent tube and they fill it with water, right? Is it correct? And the level of water will be equal at a certain height. So we have already seen that pressure depends only on z and it does not depend on xy. So this tube you can move anywhere in the plane, but this level of water and this level of water will be identical, right? Do you agree?
Yes, sir.
Yes,
Yes,
sir.
sir.
When will they not be identical?
When areas change,
When?
areas change
Fluids
amount.
of different density.
No, it
So
is
when
independent of the area actually.
the pressure or density are unequal, both ends.
No, see,
Sir, if we block the opening of a pipe,
yeah, so if you somehow block this opening and you're not venting it to the atmosphere, it will not be identical. So you have to make sure these both ends are open. And what else? There is a very latent thing that we have not discussed at all. That is surface tension. So suppose while doing his work, this region gets dirty and this region is still clean. But the dirty region will cause lot of surface tension area. So water will rise more in this region than this region. I mean that more will be very slight. It will be like a few millimeters. Huh? Even then, you will end up with having a slope over your bricks. Okay, so one has to keep things very clean. Actually, if you keep the tube diameter larger than 1 centimeter, then the surface tension effects are not prominent. So you might have studied in class 11 that surface tension is more prominent in tubes having very small diameters, right?
Yes, sir.
So as long as you prevent this small diameter condition coming into your picture, you can avoid surface tension. So manometry is still pretty common for a host of measuring devices where directly you want to get pressure differences and all. Manometry is still used. So let us see how we can derive the equation of manometry. So we had what dp dz is equal to minus rho g, where z is the coordinate system pointing up. Now let me, so because we are dealing with depth, manometry you are sort of dealing with depth. Let us change the coordinate system. Let us make a transformation from z to minus z. So we have dp dz is equal to rho g, because the minus sign that will arrive over here will cancel with this minus sign. So now the coordinate system points like this towards the bottom, and we have p minus p naught equal to rho g z minus z naught. So essentially, if you have a point over here which is P naught and the level is Z naught, the pressure at a depth of Z will be given by P equal to P naught plus rho G delta Z, or the height or the depth of that point. Okay, it's very straightforward. I think everyone has done something like this at some point or the other in JE, something like that. Okay, let me go to the next page. For recording purpose, let me rederive this in a slightly slower manner. Let us derive the equation for manometry. The equation for the variation of pressure has been defined as dp dz is equal to minus rho times g. And in the case of liquids, which is the primary domain in which we are interested in manometry, the density and the coefficient of gravity do not change with depth. Now we may integrate this over z. However, before doing that, if we have a free surface and the z pointing upwards, it is convenient for us to take a coordinate system with z pointing downwards. So let us make the transformation of z by minus z. Therefore, we have dp dz with a minus sign because we make the transformation over here is equal to minus rho times g, which implies dp dz is equal to rho g, which implies that upon integration between 2 points, P2 minus P1 is equal to rho g Z2 minus Z1. So if this is point 1 which has a pressure 1 and a depth Z1 below the free surface, and if this is point 2 which has a pressure P2 at a depth of Z2, then the difference in pressure is equal to the density times gravity times the difference in depth between the two layers. So let us consider a simple illustrative example with multiple fluids. So suppose this is the free layer and this is oil, and at a certain depth we have the free surface of the oil water interface, and I want to know what is the pressure at this point. Suppose this depth is Z1, that means that this point is Z equal to 0, this point is Z equal to Z1, and this point, so this depth is suppose Z2, meaning that this point is at Z equal to Z1 plus Z2. So let me call this point as 0, let me call this point as 1, and let me call this point as 2. Let me apply this particular equation between points 1 and 0. So I have P1 minus P0 equal to rho g Z1 minus Z0. But Z0 has been already chosen to be the origin. But let us keep this equation as it is. Let us now apply this equation between points 2 and 1. So we have P2 minus P1 is equal to, so first of all we have forgotten to write the rho of this particular oil. Let me call it as rho 1. Let me call the rho of water as rho 2. So this will be rho 1. For water it will be rho 2 g, and between points 2 and 1 this will be Z2 minus Z1. When I add these two equations, I have P2 minus P0 equal to rho 1 g Z1, and let us substitute the value of Z0 as 0 in this expression, so it will be simply Z1 plus rho 2 g Z2 minus Z1. So this expression gives us what the pressure at the bottom of the entire system will be. If I can simplify this expression further, I will have P2 minus P0 is equal to G Z1 rho 1 minus rho 2 plus rho 2 G Z2. So rho 2 G Z2 is as if the pressure at this second point, as if this entire fluid was water, because rho 2 G Z2 is as if this entire Z2, no sorry, Z2 is just the depth this, so rho 2 G Z2 is this depth, and rho 1 minus rho 2 times G Z1 is the force exerted, rather the pressure exerted at this point because of, have we missed out a sign? Have we missed out a sign somewhere?
Sir,
Yeah,
yeah, like that should be Z1 plus Z2 minus Z1, no, sir. Here in the second equation, P2 minus P1 equal to rho 2 G into Z1 plus Z2 minus Z1.
yes, because Z2 is not the depth. Good. This is incorrect. Good, very good. So then I have to eventually redo this recording. But anyway, let's continue. What a shame. So the depth of this point is actually Z2 plus Z1. So this is Z2 plus Z1 minus of Z1. That should be the appropriate answer. So this is rho 2 G times Z2 only. So P2 minus P1. So the delta P between these 2 points is simply whatever is held between these 2 points, which is rho 2 GZ, right? So if we add, so P2 minus P0 is equal to then rho 2 GZ2 plus rho 1 GZ1, and that is in fact the correct answer. So let us continue. Let us do a very simple example of measuring the difference in pressure during a pipe flow. Consider the flow in a pipe as shown. In order to make pressure measurements, we make what are called as taps. So there are small holes which are flush with the surface, and they are called as taps. In that tap, you attach a tube. You attach a tube and you fill the tube with water or mercury or with alcohol. It depends on what you're dealing with. It is good not to use mercury because of its harmful properties, but it has a good property that it's very dense, so it doesn't require a lot of mercury to operate. So now when there is a flow, okay, if we recall from our understanding of the force acting on a fluid element, the flow in this direction will be caused by a gradient in pressure such that this zone is at a higher pressure than this zone. So P1 greater than P2 will cause a flow from here to here. Now as it is going at this particular axial point and at this particular axial point, because the flow is still like this, the pressure over here will be larger than the pressure over here. If that is the case, then this particular higher pressure zone will push the fluid down and this fluid will be pushed up because the volume of the fluid in the limb will remain constant. Okay, so this is called as a U-tube manometer, not YouTube but U-tube. So then with the help of the difference in height, so suppose this final height in this limb is over here and the final height in this limb is over here. With the help of this difference in height, we can make an estimate of how high the pressure at this point is over this point. Let us do that. So at this particular point, let us call this point as A and let us call this point at B. So this particular point, the pressure we denote as PA. At this particular point, the pressure we denote as PB. Now let me just rub this and redraw. This particular point and this particular point are at the same height. What that means is the pressure at this point and this point are equal, because we've already seen that the pressure is only a function of z and it does not matter at what xy location. So given that the yellow line cuts the liquid interface over here and is enclosing the fluid over here, these 2 points are at the same pressure. So at the left limb, suppose I call it L and let me call this as R. At the left limb, P at point L will be equal to what? Suppose the density of the fluid is rho. So rho 1 and let me call this as rho 2. So because the fluid is flowing like this entire region will also filled with the fluid having the density rho 1. So pressure at point L will be pressure at point A plus rho 1 G times this particular height. Okay. So what will be this height? Let us call this height as capital H. Fine. Let me call the difference in height between the interface of the fluids in the manometer as small h. So what is the pressure at point R? What is the pressure at point R? It will be pressure at point B plus density of fluid 1 times this particular height. This particular height will be equal to capital H minus small h, because this height is h. So it will be Pb plus rho 1 g h minus h plus this particular fluid column, which will be rho 2 g small h. Now from these two expressions we can equate them, because P at L will be equal to P at R, because they are at the same height. And that implies PA plus rho 1 GH is equal to PB plus rho 1 GH minus small h plus rho 2 G small h. Now rho 1 GH and rho 1 GH cancels, and on the right hand side we have PB plus rho 1 G, rather this minus h, so instead of the plus there will be a minus sign, minus rho 1 GH plus rho 2 GH. Therefore, the difference in pressure between point A and point B is equal to rho 2 minus rho 1 times G times H. There is a small point that usually students may miss out on, is using the density of the first fluid. If I redraw the U-tube, like this, and the level of water over here is like this, and the level of water is over here, you will simply say that the difference in the height between the two fluids, that is equal to the difference in density. But no, the difference in this height times the difference in density of the fluid that is being flown in the channel, because that fluid, suppose I mark the fluid with a green color, this particular fluid will also be in this region, okay, and in this region. So it is not just the height difference h, but also the difference in density. Actually, when rho 2, suppose you use water over here, so water has a density of 1000, and if you are trying to measure the difference in pressure because of the flow of air, then rho 1 will be the rho of air, and rho of air is like 1.3 kg per meter cube. So it is so small that difference in accounting for rho 1 and not accounting for rho 1 is so small that you will hardly make appreciable error in the calculation. However, fundamentally that is still incorrect. So any doubt in this? Anyone?
You can also get the Bernoulli's theorem from here, roughly.
So I mean, I don't want to touch upon Bernoulli equation over here, because Bernoulli equation has a whole set of assumptions behind itself. With the help of, okay, so if you really want to involve Bernoulli in this, the difference in pressure over here, right, can be used to relate the difference in kinetic energies in the fluid at these 2 points. That is the best you can say at this moment.
Yes, sir.
So one request I'm making, just forget about whatever Bernoulli you have learnt in your 11th 12th. That is a very, very, very special subcase of the actual Bernoulli theorem. Okay.
Sir, if rho 1 is equal to rho 2, then PA will be equal to PB.
See, if rho 1 is equal to rho 2, actually no, PA, so it will not make any, so let us assume that rho 1 is equal to rho 2. Then the fluid sort of will not deflect at all. So you have to have immiscible fluids having the same density, right? Is that what you're trying to say?
Yes. Sir, but the fluid above has some velocity, so there will be a pressure difference.
Yeah, the moment there will be a pressure difference, everything will release. There will be no static equilibrium.
Okay.
So to have that equilibrium, this fluid has to be heavier than this fluid. The fluid inside the manometer. That is why you typically take mercury, which has a specific gravity of 13.6. That is, it is 13.6 times heavier than water. So if you're trying to measure flow of water, otherwise again the mercury will escape. Then you have no measurement.
Okay.
So should we proceed? Let's proceed. Let us consider another kind of manometer or a pressure gauge which is closed. Okay, the pressure gauge is closed, it is not open to the ambient. Like in the previous case, we saw that the two tubes were open so that the liquid could enter into the tube. The liquid is actually flowing, can enter into the tube, and then you can measure the difference in pressure. But suppose I don't want to do that. I want to measure the pressure at a single point with a single tap. Okay, so I connect a tube. I connect a tube like this. To a chamber which contains gas or an oil. So suppose it contains a hydraulic oil. So let me mark the oil with a pink color. And suppose the oil is at this point. So with respect to this center, the height is suppose 6 centimeter. With respect to the very bottom of the tube, this height is given as 11 centimeter. Now this tube contains mercury. This tube contains mercury. So suppose the red color is the height of the mercury. And there is a flow of water. So here there is water. So water will enter into this pipe and it will have something like this. So this particular height is given as 5 centimeter. This particular height of the highest point of mercury to the bottom of the tube is given as 4 centimeter. So the question is, what is the pressure at point A? If it is given that the pressure at point B is given as 87 kilopascal. Okay.
So how do we know the pressure at B? How can we control it? Like,
We can control it in various ways. You can have the membrane flexing and all these things. Okay. But suppose you know that it is 87 kilopascal. With that information in mind, how can you find out the pressure at point A? So the way to do it is rather simple. Let us look at a point which is at equal altitude. So this point. So the yellow line, all the points on the yellow line inside the fluid, of course, are at the same pressure. So then what is the, so if I call this point as left and this point as right, what is the pressure at point L? It will be equal to the pressure at point A plus the pressure due to this column of water. So 5, I mean I'm just writing down the numerical values, but these are not to be used like this. I'll tell you what exactly I mean. Plus 5 into rho water into G. Okay. What about this particular point, PR? The point at the pressure at point R will be equal to PB plus 6 times rho of oil times G plus the red fluid is mercury. This particular fluid is mercury. So now what is the height of this mercury column? What is the height of this mercury column?
7 centimeter.
It is 7 centimeter. 7 times the density of mercury times G. Now you equate these two because the pressure at point L and R are equal. So PA, so let me directly write down the result. So PA minus PB will be equal to 6 times rho 0 times G plus, not 0, it is rho oil. So 7 times rho of mercury times G minus 5 times rho water times G. But looks, all this 6, 7 and 5 were in centimeters. So we must make a into 10 to the power minus 2 to make it into meters. So this is what I was referring to. So it is, so let us take the density of water outside. So it becomes what? 6 times the density of oil divided by density of water, and let us take G outside as well, plus 7 times density of mercury divided by density of water minus 5 times density of water divided by density of water times 10 to the power minus 2 times G times density of water. So this is 1. So now we have the specific density of oil over here and the specific density of mercury over here. So specific density refers to a specific quantity where you are dividing by the density of water. So specific density of the oil is equal to the density of the oil divided by the density of water. So specific density of oil is something like, suppose it is 0.8. So 6 times 0.8 plus specific density of mercury is something like 13.6. So suppose it is 30, like this, minus 5 times G times 10 to the power minus 2 times rho W, where you can assume that rho W is 1000. So let me pull out my calculator real quick. So it is 6 times 0.8 minus 7 times 13.6 minus 5, and it comes out to be, oh sorry, 6 times 0.8 plus 7 times 13.6 minus 5, it comes out to be 95 times G 9.81 times 1e minus 2, that is the centimeter part, times the density, which is 1000. So it comes out to be equal to 9319.5 Pascal. Okay, are you getting the same answer? So then what is the pressure at point A? It will be equal to this 9319.5 plus the 87 kilopascals, 87,000. 9319.5 plus 87,000.
Yes, sir. We are getting.
So it comes out to be 96.32 kilopascal. The pressure at point A comes out to be 96.32 kilopascal. Okay.
Yes.
So very simple problem. I mean, there's nothing very complicated. And so the assignment will be littered with such kinds of problems. So let us take a quick 5-minute break. And so I'll take an attendance right now just for bookkeeping. I mean, I'm sure some people might have kept on the computer and left, right? Last time it had happened like that. So after the break, we will start studying hydrostatic forces on plane surfaces and hydrostatic forces on curved surfaces. It's a very important topic, don't miss it. So I'll be back. Let me go to my, yeah. Okay, so we now want to analyze the hydrostatic forces on submerged bodies. But before that, let us consider the hydrostatic forces on a plane surface. Okay, so before jumping into the derivation, let us first consider a very simple problem of that of a plate submerged below the surface of the water. And suppose this height is h. Okay, forget the height. Let us first physically see what is the whole deal about it. So let us first analyze the forces acting on this plate. Suppose this side you are not analyzing anything. You just want to analyze the forces acting from this side. So naturally the pressure at this point is going to be larger than the pressure at this point by an amount rho g times the length of the object. So as a consequence, if the pressure at this point is larger by an amount of rho gl, if I imagine a small differential element over here, so suppose the width of this object into the paper is b and the area is say dy or say dz. So this element has a thickness of dz. This element has a thickness of dz. And similarly, I will assume another element over here with a thickness of dz. So the area of both the elements is b dz, but the force acting on the lower element will be higher than the force acting on this element. So if I draw the diagram, the force over here will be something like this. The force over here will be something like this. And all the other forces will be like a linear variation between these two forces. As a result of which, so first of all, it is a very straightforward problem to find out the force acting on this plate. The force acting on this plate, so I can write df as the differential force acting on an element. Suppose the location is over here. Let me call that location as h as a function of z. So df at the location h will be equal to rho g times the area. Okay, so rho g z, that is the pressure acting at this point, times the area. So the area will be equal to b times dz, right? Plus we have not yet written the atmospheric pressure, plus the atmospheric pressure times b dz. Essentially the pressure at this point is equal to p atmosphere plus rho gz. So this is equal to, so if we disregard the atmospheric pressure, because it's a simple integration, it's simply PA times the area. So let's forget about it. So it's rho G Z, rho G H, rather rho G B times H B Z. In fact, let us keep atmospheric pressure. Why not? So let me now integrate the differential force to find out the total force. So it will be rho G B integral H dz plus PA times B integral dz. But Z will vary from whatever this, let me call this height as H naught to H naught plus L. So it will vary from H naught to H naught plus L. So what do we have? Rho G B. Now how does H and Z, how are H and Z related? How are H and Z related? H and Z are the same thing, right? H and Z are simply the same thing. It's just that I'm calling H as the height, but it's actually the Z coordinate. So it actually integral Z square Z dz. So it will be Z square upon 2. So it will be 1 by 2 H naught plus L whole square minus H naught square. This is the first term. Second term will be PA times B, and it will be simply Z. So it will be H naught plus L minus H naught. So what is this? This is rho G B 1 upon 2 times, so A square minus B square, what is that? A plus B, A minus B. So L multiplied by 2 H naught plus L plus PAB times L. So what is this term? What is this term? PA times B into L. So B into L is like the area of the rod itself, not the rod, the plate. So the length is L and the width into the paper is B. So the area is B into L. So this particular term is simply pressure times the area. What about this term? So it is rho G. Now what do we have? B into L is over here times, so half, and this is it gets simplified as H naught plus L upon 2. So it is rho G times, what is H naught plus L upon 2? So this,
The average pressure.
not really. H naught plus L upon 2 is not the average pressure. H naught plus L upon 2 is the location of the centroid of the object. H naught plus L upon 2 is the depth at which the centroid lies, right? Because the depth of this, of the centroid, is L upon 2, and H is the depth of the top surface, so H naught plus L upon 2 is the centroid. So this particular interpretation is rho G times the H of the centroid. So it is rho G H centroid, or let me call it H, let me call it as HC for convenience, times the area, plus the other term was PA times area. So effectively the force is equal to, if I club this, it is equal to PA plus rho GHC times the area. That is the hydrostatic pressure at the centroid of the object. So PA plus rho GHC is the hydrostatic pressure at the center of the object multiplied by the area of the object. That is the force. Is that okay?
Yes, sir.
Okay. So let's proceed. The other consideration is whether the force acts at the centroid or not. Whether the force acts at the centroid or not. Because the force at this location is higher than the force at this location, there is like a variation in the force, right? There will be a bias of the force away from the centroid. Meaning, if the forces were equal in nature, if the forces were equal in nature, okay, they were equal at all the points, then yes, we could have said that the force acts through the centroid. But in this case, there is a bias, there is a larger force acting on the bottom part of the plate, as a result of which we expect that the net force be shifted by a certain amount. That is the physical intuition that we can say. So how do we find out that point at which the force acts? It is simple. Whatever force we have just found out, if we take the moment about this point, right, whatever force we have found times the distance from this point, so let me call it as Zm, right, this should be equal to integral Z from this point times df over the entire area. So I request you to go through this small calculation. Don't be confused with this Z and the earlier Z that we measured from the top. You can call it something else. You can call this, instead of making that confusion, you can call this Y, and you can call this as Y instead of Z. It's a very simple calculation, and the end result should not surprise you at all. But you can always verify whatever we are saying by looking at the more generalized derivation, which we are going to do right now. So right now we are going to look at the generalized derivation. After doing the generalized derivation, you are in a position to do the special case of the generalized derivation. So let me draw a free surface of water. So this is the free surface of water, and let me draw a, a two-dimensional object like this. Okay. So this is the object. The angle it makes with this free surface is theta. In fact, let me that's more. Let me give it some more space. So let me call the height at a given point as h of x comma y. Well, let me define x comma y. But before defining that, we are looking at the plate from the side view. But if I draw the true shape, that is, I have to draw it in this view. You might have done this in engineering drawing. To obtain the true view, I must look at the object over here. That is, I can draw the projection or the view as seen, and it could be anything. It could be any general object. This could be the object, but the side view of this object would be a flat plate. It's a two-dimensional object. Okay. So the hydrostatic head, that is Pa plus rho g h at xy, it acts over this strip. Is this clear? First of all, the geometric interpretation should be clear. Whatever h is acting on this. Okay. Now, what is that xy that I talk about? So the centroid of the object is over here. Okay. This is the centroid of the object. And from the centroid, I define y as this and x as this. That is the local x and y coordinate fixed at the centroid. So the pressure at any point is equal to Pa rho g h x plus y. So because this is the centroid, y will point like this. And in which direction does x point? Anyone?
Out of the way.
Out of the plane of paper. Excellent. It is pointing out of the plane of paper. So now let us find out the force acting on this entire plate. So force acting on the entire plate, F, will be equal to integral P dA, where P at a given point is defined as PA plus rho GH, and this implies F is equal to integral PA dA plus integral rho GH x comma y dA. Now integral PA dA is simply PA times A, and no surprises, we have seen this in the last thing as well. So this is the magnitude of the force. Okay, first of all, this is the magnitude of the force. The direction is always normal to it, but okay, you get the point. Plus, now what about this term? So it is actually, I can take rho and g out of the integration because we have seen that for fluids, rho and g are constant. So it becomes plus rho g integral h xy dA. Now the height, can I somewhere represent it in terms of some y coordinate? I must represent this height in terms of y. So if I consider this, the coordinate originating from here, as xi, I write the coordinate as xi, right? So if the coordinate over here is xi, then xi is equal to h upon sine theta, because xi is like the slant height up until this point and h is the depth. So from trigonometry we have xi is equal to h upon sine theta. So with this we substitute it over here. So we have F equal to PA times A plus rho G integration of xi dA upon sine theta. And of course the sine theta comes out from the integral because it's a constant. So now we have integral xi dA. Oh sorry, it's xi sine theta. My bad. My bad. So what is now integral xi dA? So essentially it is like something like xi d xi dx. dA will be equal to the thickness of this strip, which is d xi times dx. So what will be this? I can write it down as xi center of gravity, not the center of gravity, but the centroid times the area. Actually xi c is equal to integral xi dA upon A is the very definition of the centroid. Okay, this is itself the very definition of the centroid, and thus we can write it as PA times A plus rho g sine theta xi centroid times the area, but xi centroid times sine theta. So xi centroid times sine theta will be what in terms of h? So suppose this is xi centroid. So xi centroid times sine theta will be the
Phi coordinate of center.
So it will be the height or the depth below the free surface of the centroid. right? Okay, so do you agree with this? So once again we
Yes, sir.
obtain it is Pa
Yes,
plus
sir.
rho g Hc times A, that is the hydrostatic pressure at centroid multiplied by the area. And this is the same result that we had obtained. So what is the important point to note about this fact? What is the most striking fact? So this result is the same as what we had obtained earlier as well. So what is the most interesting point about this result?
That is that we can keep any object in any orientation of any shape,
Exactly.
and the force acting on that would be just like rho g and the depth of the its center of mass is
Excellent, excellent.
centroid on the side.
That's exactly correct.
Yes, sir.
The orientation does not matter. You can put in any object, but you can put it in any orientation as long as the centroid, you know what the depth of the centroid is, you can find out the force. But there must surely be something which depends on the orientation of the object. There must be something which surely depends, and that
The
something,
torque.
yes, exactly, that is called as the center of pressure. So at what location does the force act on? So let me copy this diagram real quick. Let me erase some of these things. So this is the free surface of the water. So now we are interested to find out what point does the force act on. We are interested to find out at what point does the force act on. And from our preliminary discussion, we know that it will act somewhere down, somewhere below the centroid. Okay, the intuition says it should be somewhere below the centroid. So let us find that location out. So let us consider the moment of the force about the centroid. So we will have the total force acting on the object multiplied by the distance of the point at which the force acts. So let us call it YCP. So YCP is somewhere in this plane and we expect it to be over here somewhere. Okay. So force times YCP will be the moment about the centroid. So this is like the effective moment and it has to be found out. So what is the force? The force is integral PdA, but we are taking a moment about the centroid, so it will be integral YPdA. Let us substitute the expression for the pressure. So it will be Y times. So the pressure is Pa plus rho G times H times dA. Now H we can write in terms of xi, right? So this is equal to integral y Pa dA plus integral rho g y. So H in terms of xi is H is equal to xi sine theta dA. So integral y Pa dA. So Pa can come out. So it is actually integral of y dA. But what is actually integral of y dA? consider that we are finding this integral out from the centroid. So if it is the centroid, integral y dA will be
yc into a.
so yc in the centroid coordinate system is what?
First moment of
So this will be 0. No,
Zero.
this is not the first moment. This is going to be 0 because around the centroid you cannot find the net moment of y or x, because that is exactly how that centroid was found out in the first place. Okay, this is by definition of centroid. I hope you realize this.
Yes.
So the second term is, so rho g comes out, sin theta comes out, we have integral y xi dA. Now what is the relationship between y coordinate and xi? What is the relationship between y and xi? And in order to obtain that, we will write it in terms of the centroid in the xi coordinate system. Okay, so let us define. So if this is y and this is xi cg, then we have y is equal to xi cg, not this, yeah, cg, let me call it c, minus xi. So from this point you are measuring this coordinate, and from this point you are measuring this coordinate. Essentially you want to somehow relate both of these, and the only, this will not be xi cg, in fact xi cg will be that point itself. This is xi cg from this point. From this point this is going to be xi cg. So essentially if y is like this and xi is like this, then xi centroid will be equal to y plus xi. That is the idea. It is like making a simple change of coordinate. Okay. So if you substitute this, we have rho g sin theta integral of y times, so xi in terms of y is xi centroid minus y times a, and this becomes rho g sin theta integral y xi centroid dA minus integral y square dA, and this entire thing is in bracket. Now look again, xi c is a constant. By definition, xi c is the centroid location from the surface along the slant coordinate. Okay, xi c is the centroid location along slant coordinate. So the direction is along y, but it is in the opposite direction. So this term will be 0 because xi c comes out of the integration. It is again integral y dA, and this again becomes 0. So ultimately we have minus rho g sin theta integral y square dA. Now let me ask the question, what is integral y square dA?
So it is related to moment of inertia.
Yes, so it is the second moment of area about the x-axis, because it's sort of integral y square dA. Okay, it is the second moment of area about the x-axis, so it is called as Ixx. Have you studied this at some point of your life?
Yes, sir. In physics.
Yes.
First semester.
And therefore finally the expression for ycp is minus rho g sin theta Ixx upon the force. Now here is the interesting part. The force is positive, rho g sin theta, everything is positive as per convention, and Ixx is also positive because Ixx is like integral y square dA. So if Ixx is positive, and all the other terms are positive, then it necessarily means that yCp is negative. What does it mean? It means that the yCp is negative. And it means that with respect to the centroid, if y coordinate is pointing up, yCp is always going to go below the centroid. And this physical intuition we have already had. Okay? This physical intuition we've already had. Now tell me this, something to think about. This is the surface of the water. One plate is like this, another plate is like this. I mean, this is the same orientation. Okay, this. This is the centroid, this is the centroid. In which case, will the shift of the center of pressure be larger away from the centroid? In which case will be the shift larger? And why? So you think about
Sir,
it.
what is the difference between the
Can you please
orientation?
repeat the question?
Same orientation.
First one.
Yes, sir, repeat the
It's the same orientation, same angle. This is
Sir,
at
can you
a,
please repeat the question?
the question is, we have one plate at this depth, another plate at a much higher depth. We have just found out that the shift in the distance at which the pressure acts on, that is yCp from the centroid, is a negative number. So we know that it shifts down. So the question that I'm asking is whether yCp will be larger for this or larger for this,
first one, first one.
The upper one.
and why?
Upper one.
Why?
Sir, it will be same for both.
No, it will not be same. First of all,
Sir, the force acting is that because everything else is same and only force will be different for both of them.
okay, I don't know how you're answering without thinking a lot. So first of all, look at for an object which is at deeper depth, the differential between these two pressures is not going to be a lot. See, already it's at a deeper depth, so the difference in pressure, let us go to the expression. Let us rho g sine theta Ix upon f. So what was f? So f was Pa plus rho g h of centroid times area. Now as we go towards deeper depths, sine theta will not change, rho g doesn't change, Pa doesn't change, but Hc changes, right? So differential is still the same. What I said was wrong. So the Hc increases. So for an object, so this is the expression for yCp minus. So for an object which is at a deeper depth, this magnitude will be larger, right? So if the denominator increases, so Ixx also doesn't change because the shape of the object doesn't change. As long as the shape of object doesn't change, Ixx is not going to change. And if that is true, then if the denominator increases, then the yCp will reduce, meaning that the shift from the centroid towards a lower point will be less for an object at a deeper depth. So an object at a deeper depth, the centroid and the center of pressure will be close. They will not coincide, but they will be close. At infinite depth, they will coincide. Is it clear?
Yes, sir.
As a homework, this is going to be your homework. Derive an expression. Can you guess the homework? Who can guess the homework? Who has that skill? Who can guess the homework? Something. Who can make a guess? Wild guess.
Difference in the YCP for both sides.
No.
If
That is a good
they
guess,
make
but that is not what
For
I
a
had in mind.
square,
I just want you to derive an expression for the x center of pressure. We have obtained an expression for the y center of pressure, right? Now you must find out an expression for the x center of pressure, meaning from this centroid, how far does the x coordinate where the effective pressure acts on shifts? We have already found out ycp, so xcp will be somewhere on the axis of this. It will be somewhere, but what is that shift? I want you to find out what is that shift.
So 0.
No, it will be not zero.
Sir, 0.
No, it cannot be zero. Because if the body is symmetric about this axis, only then it will be zero. See, I can have a body which is like this. It has more area over in this part of the axis than in this part of the axis. So it will shift on this part. Are you understanding?
Yes, sir.
If the body were to be
Yes.
perfectly symmetric, if this area and this area content were same, then it would not shift. So your intuition,
Sir, but it will still be equal to, sir, it will still have the same x as the centroid, right?
no, it will not have the same axis center. There will be a shift from the centroid. So let us imagine two objects which are submerged in water. It will be clear. It will be clear to you. One object's cross section is something like this. Okay, and one object's cross section is something like this. The centroid is somewhere here, but more pressure is acting on these regions. Okay, less pressure acts here. Centroid has shifted because of the larger distribution of area over here. So about this centroid also larger pressure acts in this region, which has a larger x. So the x will shift towards this. So I'm telling you the answer. So basically it has become from find out the value or find out an expression it has become a question of prove that. Oftentimes I see students have easy time in proving something rather than finding something. So prove that the xcp is equal to minus rho g sine theta ixy, and anyone who could have guessed that ixy would come into the picture, I give you 5 extra points in my head. Okay, divided by the force, which is the P at the centroid times the area. PC is the P at the centroid. So this is P atmosphere plus rho G at centroid. And what is IXY? So if this is the centroid, this is Y, this is X. What is the expression for IXY?
X, Y, dA.
XYD.
Yes, it will be integral X times Y dA. So it will follow the same train of thought as the shift in Y. Okay, it will follow the exact same train of thought. And you will see that you will find an expression, and the more symmetric it becomes, so integral so ixy for a symmetric object is 0, and that is why it will not shift for a symmetric object. And as you have departure from symmetry, you will keep on getting a different shift. And actually what someone had just pointed out, if as long as the object breaks symmetry and has a slightly larger area towards higher pressures, that x will shift, and all that information is sort of encoded in this. You can have things which, I mean, so try to realize the conditions at which ixy will be 0. For any other non-symmetric object, it will be 0. Okay, for any other non-symmetric object, the location of the centroid with respect to any other coordinate will be found out as x times dA. Okay. And x times dA is going to be 0 because we are taking the moments about the centroid. But don't worry about whatever I just said. Try to prove this with the help of the information gained in the previous derivation.
So we can easily prove that.
Yeah, I mean it's just you have to.
Y, dA will be same. We just have to change the moment. So
Yeah,
moment
just,
will be df into x. So we will get ixy.
but still it's worth doing it, writing all the steps down. Nothing wrong in that. But yeah, I mean, it's nothing complicated. See, you are very quick student, so you are telling me, but someone who might have not have grasped the initial derivation, so for him, he has to go back to the original derivation. He has to go through the derivation. He has to do the derivation.